thanks for watching, and today I'll do something really cool and very relevant. I will calculate the volume of a ball of radius r in n dimensions. And I will do this purely using calculus and maybe multivariable, so calculus as well. So let's call this VNR. It's like NPR but with a V. Okay, be the volume of the ball, of center X and R in Rn. Notice it doesn't really depend on X at all, so let's just say it's 0. So it's just the volume of the ball centered at 0 and of radius r. Okay. So for example, V1 of r, that's the ball of radius r in R1. In other words, it just becomes this interval. So the volume is just the length of the interval, which becomes 2r. And then V2 of r, it's our usual unit disk, so pi r squared. V3 of r is 4/3 pi r cubed. And the goal is now to find it in general, for general n. And you'll see it's very interesting. So, not that other things aren't interesting, but it's very good. So first of all, I want to make a little, simplification. I'm telling you that this r doesn't really matter. So I'm saying for the rest of the proof it doesn't really matter, because I'm claiming that the volume of a ball of radius r in Rn is just r to the n times the volume of the ball of radius 1. So in other words, if you compare the ball of radius 1 and the ball of radius r, then the volume is precisely r to the n times the unit volume of the unit ball. And there are two ways of doing this. One is the amazing linear algebra way, where you just have a linear transformation t of x equals to rx. Okay, and that would work. You could use determinants and everything, but I'm guessing some people don't know linear algebra yet, so let's do it using multivariable calculus. And why is that? If you take the volume of an object, that's the same thing as integrating the function 1 of that object. So in single variable calculus, you learned that the integral of 1 is just the length of the interval, which becomes the volume of the interval. So here, this is true. The volume of an object is always the integral of 1. And now, I want to use a change of variable, namely, yi equals to xi over r. Okay, so in other words, y1 is x1 over r, y2 is x2 over r, etc., etc. And the nice thing is, if you calculate the Jacobian, you get, again, dy1, dy2, dyn. That becomes partial y1 over partial x1, partial y1 over partial x2, partial y1 over partial xn, okay, etc., partial yn over partial x1, partial yn over partial xn. And again, you take the absolute value of the determinant of that, dx1, dxn, so it should be this of determinant of that. But the nice thing is, this matrix simplifies. So remember, basically, y1 is x1 over r, y2 is x2 over r, etc., etc. So the nice thing is, only the diagonal terms matter, and you get absolute value of the determinant of 1 over r, Okay, so yeah, 1 over r, 0, 0, 0, 0, 1 over r, dot, 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 1 over r, okay, dx1, dot, 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 dxn. And then if you take the determinant, you get 1 over r to the n, dx1, dxn. So this is positive, so no need to take the absolute value, which is 1 over rn dx1 dxn. So you get dx1 dxn equals to r to the n dy1 dyn. So we get the volume becomes, so if one integral of, before I forget, what happens to the ball of radius r when we do this change of variables, yi is xi over r. It just becomes, of course, the ball of radius 1. So what this becomes, it becomes Vn of 1, integral of 1 of Vn1 of r to the n dy1 dyn. But then if you take the r outside, the r to the n, it becomes r to the n times the integral of 1 of this object, which becomes r to the n Vn of 1. So in other words, the volume of a ball of radius r is just r to the n of a volume of ball of radius 1. Which explains, for example, that in 3 dimensions, you have 4/3 pi r cubed. Or in 2 dimensions, you have pi r squared. Okay. That's good. It means that because we have this formula, from now on, let's assume that r equals to 1. Because once we found the volume of the unit ball, we can just multiply everything by r to the n to get the volume of the ball of radius r. So the point is, assume r equals 1. Okay. This was the prep material, unfortunately. Now we'll do the core of the matter. Core, like the ball. Okay, and here comes a super clever idea. So step 2 is actually to approach this problem like the disk method in single variable calculus. So here's a clever idea. Suppose you have, again, the ball in Rn, okay, of radius 1. Okay, so that's 1. If you want, that's minus 1. And the x-axis just becomes the first variable, and the y-axis becomes all the other variables. Okay. Suppose that you just slice this ball. Okay, so again, maybe here, think of 3 dimensions. If you slice the ball in 3 dimensions, you actually get a disk, which is a ball in 2 dimensions. And in that way, you can reduce the volume of the ball in Rn to just the volume of the ball in Rn minus 1. So more precisely, if you take hyperplanes if you want, so object of dimension Rn minus 1, then the slices with those hyperplanes are in fact balls of dimensions n minus 1. Okay, and let's figure out what that is. Now notice, in fact, all we need to do is to find, the volume, is to use, in fact, just the disk method in single variable calculus, because all we need to do is integrate, from minus 1 to 1, the area of each slice. So, by disk method from single variable calculus, what does the volume become? So Vn of 1 becomes the integral from minus 1 to 1 of the area of this. Let's call this A of x1, x1 dx1. And let's figure out what the area is. So what we know is that this is a ball, it's a ball in Rn minus 1, and let's figure out what the radius is. So here, you have x1, okay, so this is, let's say, from 0 to x1, and you have the radius. Okay. The radius, but what exactly is the radius here? Notice the distance from this point to this point is precisely 1. So this distance is 1 because the original ball has radius 1. This distance here is x1. So r really becomes square root of 1 minus x1 squared. So because the radius is square root of 1 minus x1 squared, the volume becomes whatever the volume of the ball is in Rn minus 1, which by definition is Vn minus 1 of R, which becomes Vn minus 1 of square root of 1 minus x1 squared. So, in the end, what we have to do is integrate from minus 1 to 1 of Vn minus 1 square root of 1 minus x1 squared, okay, dx. And now, you might say, what in the world, how in the world can we do that? Notice the scaling law I shown you, that the volume of a ball of radius r is just r to the n times the volume of the ball of radius 1. It holds for any n. Before I did nothing special with the fact that it's n. In fact, it holds for n minus 1, which means that the volume of this ball is whatever this chunk is, raised to the power of n minus 1, times the volume of the unit ball in Rn minus 1. So that in the end becomes square root of 1 minus x1 squared to the n minus 1 of Vn minus 1 of 1 dx1. So much, much, much better to handle. Okay? And then, lastly, we can take this out. And instead of x1, you write x. So Vn minus 1 of 1. Okay, integral from something to something of, if you want, 1 minus x squared n minus 1 over 2 dx. And lastly, one little thing. This is an even function. So the integral from minus 1 to 1 is 2 times the integral from 0 to 1 of this thing. Great. So in other words, we reduce the problem of finding our volume to finding the volume in one dimension lower times this really ugly integral. And now our goal is to just calculate that really ugly integral, and you'll see it uses purely calculus techniques, which is what makes it nice. Okay, so what did we have so far? Vn of 1 becomes Vn minus 1 of 1, 2 times that, times the integral from 0 to 1 of 1 minus x squared to the n minus 1 over 2 dx. And now let's use a little change of variables as if this wasn't complicated enough. Let's use u equals to x squared. Then du is 2x dx, which tells you that dx is du over 2x. But again, x is positive, because x is between 0 and 1. So du, it just becomes 2 square root of. So the point is Vn of 1 becomes Vn minus 1 of 1 times, again, 2 from the integral from 0 to 1 of 1 minus u, n minus 1 over 2, 1 over 2 square root of u du. And the 2's nicely cancel out. Good job, myself. And that equals to Vn minus 1 of 1 integral from 0 to 1 of 1 minus u to the n minus 1 over 2 times u to the minus 1/2 du. And you might say, Payam, why did you take this complicated integral and made it even more complicated? I do have a point, because even though this integral is much more complicated, it's actually one of those known integrals that, to be honest, I've never heard before, but this is what's called the beta function. Okay? It's d beta n minus 1 of b of 1/2 and n plus 1 over 2. Beta is the beta function. B of xy is defined to be the integral from 0 to 1 of t to the x minus 1, 1 minus t to the y minus 1 dt. The beta function. It's like the beta cell of math. And in fact, whoever says beta function says gamma function. In fact, this function and the gamma function that we know are related. So step 3, here's a claim. Beta of x comma y is in fact the same as gamma x, gamma y over gamma of x plus y. And of course, I'll prove this, but in case you don't know, the gamma function is defined to be as follows. Gamma of x, that's integral from 0 to infinity of e to the minus u to the x minus 1 du. So the input x goes in this exponent of u, and this is very nice because it's really the real variable generalization of the factorial function. And if you look at my video about fractional derivatives, I'll talk about the gamma function a bit more. Okay, and you might say, why is this true? Why is the beta function, equals to gamma x, gamma y over gamma x plus y? It has to do with the clever change of variables. Why? Well, let's calculate the gamma x times gamma y. And let's see what happens. Gamma x times gamma y, by definition, that's e to the minus u to the x minus 1 du times integral from 0 to infinity e to the minus v to the y minus 1 dv. And if you put those together, and if you Fubini it, it's integral from 0 to infinity, integral from 0 to infinity. So the e of u minus v combines to get u plus v, and then you get u of x minus 1, v of y minus 1, du dv. Okay. And do not ask me how I came up with the following change of variables. It's a little miracle here. You just let, magically, I literally pull out some rabbits out of my hat. Let's define z and t so that u equals to zt and v equals to z minus tz. So it's really t, z times 1 minus t. So then, what do we have? A du dv, right? Now let's calculate the Jacobian. So that's the absolute value of the determinant of, again, du over dt and du over dz, du over dt, dv over and dz, dvd, okay, dv over dt. So if you do that and you use our definition, it becomes the absolute value of the determinant of. So zt, if you do it with respect to z, you get t, and then z, and then 1 minus t, and then minus z, okay, which becomes, minus tz minus z plus tz. Again, I forgot, times z dt. But then it turns out that in fact both those, that z is non-negative, and the reason is we know that u is non-negative, so either z and t, they're both positive or they're both negative. But because we also know that v is greater than or equal to 0, worst case scenario, z would be negative, and then 1 minus t would be negative, but then t would be greater than 1. I guess, yeah, t would be greater than 1. But then, if t is greater than 1, it's positive. So t is positive, and therefore z also has to be positive, which would be a contradiction with z being negative. So in particular, after all this gibberish, we know that z is greater or equal to 0. So if you take absolute value of minus z, in the end, you're just left with z dz dt. So the point is the Jacobian becomes very easy to calculate. And then just one little remark. Based on that, as I said, we know that z is greater or equal to 0. So our region becomes z is greater or equal to 0. Okay, and z could have any value. But here, because z is greater or equal to 0 and v is greater or equal to 0, we know that 1 minus t is greater or equal to 0. So t has to be less than or equal to 1. And again, also by this relation, z is greater or equal to 0 and their product is greater or equal to 0. So t is actually between 0 and 1, which means our bounds of integration will be from 0 to infinity for z and from 0 to 1 for t. So in the end, we get the following. We get gamma of x times gamma of y. It equals, now to our new bounds, so integral from 0 to infinity, integral from 0 to 1, our Jacobian, z, if you want, dt dz. And now let's see what happens to our original function. So e of minus u plus v becomes zt plus z minus zt. Now I'm hungry for pasta, because zt pasta. So it's, which again simplifies, so maybe that's the most exciting part of this integral. Okay, and then we have zt to the x minus 1, z 1 minus t to the y minus 1 times z. And so we can simplify that, as I said, integral from 0 to infinity, integral from 0 to 1, e of minus z, and I guess let's do that. So z to the x minus 1, t to the x minus 1, z to the y minus 1, 1 minus t to the y minus 1, and again z because of the Jacobian, dz. And then let's just put all the z's together and all the t's together. So this really becomes integral, and also here, integral from 0 to infinity of e of minus z, z to the x minus 1 plus y minus 1 plus 1. So the point is, if you add the exponents, you're just left with x plus y minus 1, okay, dz. And the integral from 0 to 1 of just t to the x minus 1 and 1 minus t y minus 1 dt. And just one little thing, I did skip a step, because how do you know that you can separate out those integrals? Well, think of it as the following. Just think of it of putting this function that purely depends on z inside of that integral. So you really get integral from 0 to infinity, integral from 0 to 1 of this chunk multiplied, which is precisely that. And then, in case you're still watching, okay, this turns out, it looks like gibberish, but they're actually familiar functions. This is precisely, if you think about it, as the gamma function. at x plus y. And this thing that seems unfamiliar is actually this beta function. So b of x comma y. So what did we have? Gamma of x times gamma of y equals to gamma of x plus y, b of x comma y. So in other words, if you solve, for, what is it, b of x comma y, so beta function becomes gamma of x, gamma of y, over gamma of x plus y. Okay. All right, and we're not done. Actually, we're almost done. Okay. So we have the formula, and remember our integral could have been written in terms of b of x comma y. So the last step, what did we have? So far, we had the volume of the unit ball in Rn equals to volume of the unit ball in Rn minus 1 times the beta function. So you get beta 1/2, beta n plus 1 over 2. But then we had this nice relation that the beta function is the same as the gamma function at 1/2 and the gamma function at n plus 1 over 2 over the gamma function of the sum of the two, which becomes n plus 2 over 2. But then the question is, what is gamma of 1/2? It's actually something very familiar. So by definition, gamma of 1/2 is the integral from 0 to infinity of e to the minus x and x to the 1/2 minus 1, which becomes x to the minus 1/2. But the nice thing is we can evaluate this, because let u be square root of x, then du is, if you want, 1 over 2 square root of x dx, which appears precisely here, except for a factor of 2. So you're left with 2 times the integral from 0 to infinity of e to the minus u squared du. But that's the same, again, by evenness, as the integral from minus infinity to infinity of e of minus u squared du. And in another video from another channel, I have shown that this equals to square root of pi, which gives you, in the end, a recursive formula for the volume of the ball. So Vn of 1 is square root of pi Vn minus 1 of 1 times the gamma function, so n plus 1 over 2, divided by gamma of n plus 2 over 2, which is n 1/2 n plus 1. Okay, if you like recursion, then you're done, but you may not be satisfied by this. So let me write this down in a more explicit form, and you'll see it'll be a nice telescoping product. So step 5. What did we have? Vn of 1 is square root of pi gamma of n plus 1 over 2 over gamma of n over 2. I guess, let's say n plus 2 over 2, Vn minus 1 of 1. But then, you can just, this is almost like a geometric sequence, almost, and you can just use the same formula, but replacing by n minus 1. So that basically equals to square root of pi gamma of n plus 1 over 2 over gamma of n plus 2 over 2. And then just do the same thing, square root of pi gamma of n over 2 over gamma of n plus 1 over 2. And then just do the same thing again, square root of pi gamma of n minus 1 over 2 over gamma of n over 2. And do this n times until you're left with square root of pi gamma of 1 over gamma of 3/2. And now notice the exciting thing happening. All those things here, the cross, or I guess the diagonal terms, they all cancel out. So boom, 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 boom. And then all you're left with are the square root of pi's, which you do n times. So square root of pi to the n, okay, times, I guess, gamma of 1 over gamma of, I guess, n plus 2 over 2. But then gamma of 1, if you'd like, that's the integral from 0 to infinity of e of minus x times x to the 0 dx, and that equals to 1. So in the end, you get that the volume of the unit ball equals to pi n over 2. Of course, because you can't have my name, you know, in such an awesome video. Okay. And that becomes gamma of, now you can write it as 1 plus n over 2. And then, well, we're almost done. We found the volume of the unit ball in Rn. What about the volume of the ball? So remember an hour ago, I told you that it scales like r to the n. So we get pi n over 2, gamma, I guess, n over 2 plus 1 times r to the n. Ta-da! So after this long battle, we're actually done. And in case you're curious, I might do this in another video, but if you want to find the surface area of the sphere, you actually just differentiate that with respect to r. But I might do it with another method in another video, as I said. And if you like this, and you like math, please make sure to subscribe to my channel. Thank you.
Yay!
Yay!
This is not a whole lecture. This is just one problem.
Yeah. Yep.
Yeah. Oh yeah.
Yep.
Oh yeah. So some viewers would like to ask you about your shirt. Why there are so many chalks? Every
Because
single time after the
today
end.
I did one whole lecture, and I did, let's see, 3 videos. And,
Yeah.
like with this length. So yeah.
It is.
It's a new fashion trend for the winter.
This is the upside down version of Dr. Payam. And this is the Dr. Payam.
It's DK Payam fashion.
Yeah, okay.